go over the first exam of the semester. As a good practice and as a good reminder, what I'm going to do is I'm going to present the picture of the question for you so you can stop it there, solve it, and then I'll go over the answer. I won't necessarily give you enough time in the video, so please stop the video, solve it, and then restart it when you're ready to see the answer. The first one is the easiest question in the exam. So how many carbon-carbon bonds are in one molecule of hexane? And it's as simple as drawing hexane, which is a 6-carbon chain, 1, 2, 3, 4, 5, and 6, and then counting. So I have 1, 2, 3, 4, and 5. So the answer is 5. For the second question, calculate the number of unsaturations for this molecule. Remember that we use a formula for it. So there are two ways of talking of unsaturation. Remember that unsaturations are double bonds or rings, and that triple bonds can count twice. So I'm going to say that again. So a double bond is one unsaturation. A triple bond counts as 2 unsaturations, and a ring counts as 1, right? So 1 unsaturation for the double bond, 2 unsaturations for a triple bond, and 1 unsaturation for a ring. But when we are given the formula, just as this one here, what we do is something else. And what we do is that we use the formula. I'm going to remind you of the formula. That is 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens, and the oxygens don't count. Then you will divide these by 2. In the formula, you would add the number of nitrogens. In this particular case, we don't have any nitrogens. So if we apply this formula to this formula that we are given, it's 2 times 8 times 2 minus the number of hydrogens, which in this case is 6, minus the number of halogens, in this case is 2. The oxygens don't count, and we don't have nitrogens, and then we will divide that by 2. So it's 10 divided by 2, that's 5. So the answer is 5. In question 3, we're asked which one is the major contributor to the hybrid. The major contributor to the hybrid is going to be the most stable of the resonance structures. You are not, in this particular question, you're not necessarily given the charges. So you have to recalculate the charges. If you do that, you see, for example, in molecule A, you have a carbon that is connected to 1, 2, 3, and then the 2 hydrogens, so that's 5. And so we will do 4, that it's the number of electrons that carbon usually has, minus 5, and the answer is minus 1. So that's why we will have a minus. For nitrogen, nitrogen usually has 5 electrons, but in this case it has 4, so we get a plus. Same for this nitrogen, and in this oxygen, oxygen usually has 6, but in this case it has 7, so we have a minus 1. So molecule A has 2 positive charges and 2 negative charges. If you do the same for molecule B, you end up with a plus there and a minus here in the oxygen, and molecule C doesn't have any charges. Now, molecule C is the most stable one. It doesn't present charges, so that will be the major contributor to the hybrid. Which of the following functional groups does not have a carbonyl? Well, at this point, you would have to memorize the functional groups and what each one means. Carboxylic acid is this one, right? So remember, this is a carboxylic acid, and don't get this confused with a ketone and an alcohol. When they are right next to each other, they are carboxylic acid. Be careful with this because these actually will be an alcohol and a ketone. But in here, the alcohol part and the carbonyl part are connected to the same carbon. So this is a carboxylic acid, and the one on the right will be a ketone and an alcohol. This was just on the side, not what the question was asking. Then we have an amide. Amide is the amine equivalent of the carboxylic acid. So we will have two R's, so R1 and R2. An ester is this, and at this point, again, just memorize it. An ether is this one. Ether is the one where you have the oxygen right in the middle, and then an aldehyde is this one right here. Okay, so the only one that is not connected to a carbonyl or that doesn't present a carbonyl, it's the ether. It's this one right here. This question asks, the carbon-carbon single bond in the following molecule is formed by the overlap of which two orbitals? First of all, you have to identify which one is the single bond in this molecule. The only single bond in this molecule, CC single bond, is that one. And now you have to look at the carbons that are forming that bond. So the carbon on the left is connected to a double bond. It's connected on the right to another carbon, and then it has a sigma bond to a hydrogen. So it's connected to three things that will be sp2 hybridized. On the right side, I have a carbon connected to another carbon on one side and the nitrogen on the other side, so that will be sp, only connected to two different things. Remember, sp2 hybridized has an angle of 120 and sp hybridized has an angle of 180. So the answer for this one is going to be B, because sp2 sp. What's the IUPAC name for the following compound? First of all, you have to identify the longest possible chain. The longest possible chain in this case is going to be this one, right there. Now, everything else that comes out of that chain, those are going to be substituents of the chain. So now you have to make a decision. Am I going to start numbering like this? Or I'll go the other way around. 1, 2. In both cases, you have 8 carbons, which is what we wanted, but we want to know if we're going to start from the right or from the left. So if we go with the black numbering, 1, 2, 3, 4, the first substituent falls in position 3. But if you go with the red one, you see the first substituent will fall in position 2. So that is telling us that we have to start numbering from the right. Once you've identified those two, now we can actually name the molecule. 1, 2, 3, 4, 5, 6, 7, and 8. And so that's the main molecule. So we know it's going to be an octane. And then we have at position 2, we have a methyl. So methyl, that is at 2. At position 3, we also have a methyl. At position 6, we also have a methyl. And at position 5, we have an ethyl. So I can group those three and call it trimethyl. And so here I'm missing an H. And the bottom one is going to be the 5-ethyl. Because the E goes before the M in the alphabet, the E is going to go first, even though it has a 5. So the answer is going to be 5-ethyl 2,3,6 trimethyl octane. And that's the choice D. If we go back to our choices, that's D. The next question is asking about the S character of the sp2 orbital. To do that, remember we have an sp2 orbitals here in the S is like if you had a 1, so in total you have 3 orbitals. And one of them is S. So if you put this in the form of a fraction, 1 out of 3 will be S, which is equal to 33%. Remember that for sp3 hybridized, the S character is going to be 25%, and for an sp, the S character is going to be 50%. And the more S character that a molecule has, the more, or that an atom has, it's going to make it more acidic. The next question is asking what's the conjugate base of sulfuric acid? So sulfuric acid is this molecule right here. You have to know that the conjugate base is the same molecule minus a hydrogen. So the answer is HSO4 minus. In this question, we have to choose the correct equilibrium arrow to predict the position of the equilibrium, if it goes to the right, to the left, or if it's an equilibrium. So option C is out of the question because that's for resonance structures. And it's very likely that the reaction is not in equilibrium, so we also can discard A. So we are in between B and D. To figure out if it's B or D, to see if it moves forwards or backwards, we need to figure out what is the reaction that's happening. So first of all, you need to identify that this right here is the base and this is the acid. This is an acid-base reaction, so what is going to happen is if you have your CH3OH there, that is going to come and get the proton. So now on the product side, we're going to have NH4 plus, which becomes our conjugate acid. And here we're going to have CH3COO minus, and that's our conjugate base. To figure out where the reaction is going to go, we know that the reaction will favor, so reaction will favor the weaker species. Either if you compare the two acids or the two bases. The easiest way to figure out where the equilibrium will go is to go to the pKa table and compare the pKa's of both acids. If you do that, you will be comparing the pKa of that and the pKa of the conjugate acid. The pKa of the acid is 475 of the carboxylic acid, and the pKa of the NH4 plus will be 9.4. The higher the pKa, the weaker my acid, so the reaction will favor the product side. In question 10, we're being asked what's the hybridization of the labeled atoms. So the first, maybe the easiest way to see it is if you draw it out, just like that. So you see that the first carbon is connected to 4 different atoms, or 4 atoms rather than 4 atoms. So that would be sp3. And the second one is connected to 2, so that's sp. And the third one is connected to also 2, so that's why it's sp. So the answer for that is C. In this question, we're being asked to calculate formal charges. To do that, we're going to look at the central atoms, which are the oxygen and the bromine. Oxygen, in the periodic table, it has 6 you can see in the periodic table that it has 6 valence electrons, so it's 6. But in this particular case, it's connected to 1, 2, 3, 4, and 5, right? It owns 5. So that's why 6 minus 5 is plus 1. And the boron, it usually has 3, so it has 3 valence electrons, but in this case, it owns 1, 2, 3, and 4. So that's why it's minus 1. The answer for this question is C. In this question, we are asked about the functional groups. So it has an alkene skeleton, that's true. But now let's identify the other functional groups. So here there's a ketone. This is an alkene. This right there is an alkyne, a triple bond, and that's an alcohol. So the answer that has all those choices is D. Question 13 asks, which of the following is not a conjugate acid-base pair? So remember that an acid-base reaction, you have the acid that has one H plus the base, and the base will be taking that hydrogen, and then you get conjugate base plus conjugate acid. What I'm trying to say is that only one hydrogen is moving. The pair will be the one where there's only one hydrogen difference in between the two species. And for the choice B, there are 2 hydrogens being lost because we are comparing that versus that. So in this case, there are 2 hydrogens that are missing. So that's why the answer is B. In this reaction, we need to identify the species. So maybe you can identify what's happening, or you can simply realize that this species right here, the functional group is a conjugate acid, and if a carboxylic acid, sorry. So the carboxylic acid is the most acidic species, or is the most acidic functional group. So that's usually going to be your most acidic molecule. So that's if that's the acid always reacts with a base. So then that makes this pyridine here your base. The reaction that is actually happening is that base comes and gets the electron, and that's how this now becomes, if this is the base, this becomes the conjugate acid, and if this is the acid, this now becomes the conjugate base. All right. The conjugate acid of ammonia, so you must know from general chemistry that ammonia is NH3. So the conjugate acid by definition will be this species plus 1H, so that will be NH4. And remember that we'll have a plus because the N is usually connected to 5 electrons, and in this case is connected to 4. So 5 minus 4 plus 1. That's where that plus is coming from. So how many unsaturations does this molecule have? In an example that we saw at the beginning of the exam, we had to use the molecular formula to figure out how many unsaturations, but in this case it's simpler. So remember that one unsaturation was a ring, or a double bond, or a triple bond, but the triple bond counts twice because there are 2 pi systems involved. So in this case we have 1 ring, 2 rings, and 3 rings. We have 1, 2, 3, 4, 5, 6, 7, so 3 rings, 7 double bonds, and I have a triple bond here that counts as 2 double bonds, so that will count as 2 more. So the total, it's 12. The answer is B. We need to select the strongest base. Remember that these 2 species right here, they are ionic species. So C, it's actually these. These are ionic species. They don't have a covalent bond in between them, the same as Na plus OH minus. Right? So carbon is more uncomfortable carrying that negative charge, so that makes it a stronger base because it's higher in energy. Another question asking us where the equilibrium is going to go. So I went over it in a previous question about the basics of it, but now in this case, instead of comparing the 2 acids, we're going to compare the 2 conjugate bases, or the 2 bases, right? We're going to compare the base right here with the conjugate base. So if we do that, we see that this one right here is going to be more stable because that Cl is pulling electron density away from the negative charge. So that's stabilizing this base, it's stabilizing the base, so it makes it the weaker species of the pair, and that's why the equilibrium will go backwards. The answer is A. For question 19, I know it's tricky, and I know that most of you were between B and D, but remember that triple bonds are sp hybridized, and if they are sp hybridized, they have to be 180 degrees apart. So that's why I told you that you never you can draw the triple bond being bended just like that. That's a no-no. So that's why the answer is D. This question asks about the relative acidity of each of the following compounds. In other words, they are asking us which one of these molecules is more willing to donate one hydrogen. To figure out the answer, probably the best way is to draw the three conjugate bases. And compare them. You see the carbon having that negative charge is highly unstable, is highly uncomfortable having that negative charge because it's the least electrophilic of the electronegative, sorry. It's the least electronegative of the three atoms that we are comparing. So because of that, carbon is going to be the one that is higher in energy. So the C minus is going to be higher in energy. Then we have N minus, and then we have O minus. What this means is that molecule 2 is the one that is more likely to be giving out that hydrogen connected to the oxygen, because it's the one that if it gives it away goes into a more stable state. And because of that, 2 is the one that is going to be the most acidic. Following the same logic, 3 is going to be the one that is most unstable, carrying that negative charge. So this carbon is very unlikely to give any of the hydrogens that are connected to it away. So that's why the most acidic is going to be 1, then, sorry, the most acidic is going to be this one right here, 2. Then the second one is this one, and the third one is the one with the carbon. So the answer for that is C, right there. What's the formal charge on the carbon atom? So that carbon is connected, it owns 1, 2, 3, 4, and 5. Carbon is usually connected to 4. It has 4 valence electrons, but in this case it has 5. So the charge is going to be -1. The answer is C. In here we need to identify the roles of each one of these molecules. So to understand those roles or to identify them, we need to understand what's the reaction that's happening. So in here you see this species is the one that is negatively charged. So even though water can act as both an acid and a base, in this case water is less basic than NH2 minus. So let me draw it out. Well, actually, water, you know that water doesn't look like that. Water looks like that. And now I have the base that can go and grab the protons, and so that will give me the OH minus and the NH3. So this is the acid, this is the base, this will become the conjugate base, and this will be the conjugate acid. So because they are asking us about the strongest base between the two bases, we are comparing species B and species C. The strongest of them two, we're comparing an N minus with an O minus. Oxygen is more electronegative, so it's more comfortable carrying that negative charge. So N is going to be more reactive and therefore is going to be the most basic of the two. In question 23, we're being asked which one of these is not a true statement. So the Lewis bases and the Bronsted-Lowry bases, they are the same because they are all going to be the species that have negative charges. So for example, not negative charges, but electron density. For example, that one that is both a Lewis base because it's electron dense and a Bronsted-Lowry base. It's ready to go and get the protons. That statement would not be true for the case of acids. So pause here and think about if you think that you could not say all Lewis acids are also Bronsted-Lowry acids, and think why that statement will not be true. But for bases, that statement is okay, is true. So it's okay to say this statement for the Lewis bases versus the Bronsted-Lowry bases, but it's not okay to say it for the acids. And the reason why you cannot say it for the acids, it's because Bronsted-Lowry acids, they have hydrogens, but Lewis acids don't always have hydrogens. For example, this species right here, that's a Lewis acid because it can accept electrons. Well, that one. Let's do aluminum chloride. So aluminum can accept the electrons, and that's why it's a Lewis acid, but it doesn't contain hydrogens. So that's why this is the false one. For question 24, you have 3 hydrogens in there, 2 hydrogens there, and there are no hydrogens right there because that carbon is already connected to 4, it has 4 bonds. So you have 3 and 2 and 2 and 3. The answer is going to be 10. Primary carbons are carbons that are connected to only one R. So for example, that will be a primary carbon. So in this case, we have 1, 2, 3, and that's it. So we have 3 of those. Secondary carbons are the ones that are connected to 2 R's. So then it would be this. To give you an example, this would be a secondary carbon, this one 2, this one 2, this one 2, and a tertiary carbon is the one connected to 3 R's. For example, this one right here will be tertiary, and this one right here will also be tertiary. And for the bonus question, the trick here was to realize that the longest possible chain was the ring. This ring in the middle is your longest possible chain, because look at what happened. If you try to pick, let's say, these as your longest possible chain, we have no way to describe that bridge there in the middle. That is not a substituent really, so we cannot define that in any other way. So once you decide that this is your longest possible chain, which is a 5-member ring, then this option is the only one that had a cyclopentane. Then if you want to talk about the position of the substituents, the lowest one is going to be the one that has the 2 substituents, that is this one right here. So that's going to be your number 1. And then you can go clockwise or counterclockwise, right? So clockwise will be this side, counterclockwise will be that side. You would go counterclockwise because the second substituent will be right there. If you go into the other direction, your second substituent will be 1, 2, 3. It will be 2 over. Whereas if you go towards the right, your next substituent is right next to itself.